We also talked about inductance of a coil of wire, denoted by L, is basically the flux of magnetic field that goes through the wire from its own current divided by I. If you put a current through it and it has a magnetic field and the magnetic field goes through the coil itself, you can define L, the inductance, as phi b over I. And if there is n turns and phi is only for one turn, then we can multiply this by n, say that it's n times phi over b. But then we said that when current changes in an inductor, it has a back electromotive force, which is given by negative L di over dt. Then we calculated the inductance for a solenoid. We said that inductance per unit length of the solenoid is equal to mu naught n squared times area. It is only geometrical. It depends only on geometry of the coil. We also talked about if you have a circuit like this, you have a switch, you have an inductor here, and you have a resistance L, R, and a battery with voltage V. We said that when you close the switch, this inductor doesn't let the current go suddenly to maximum. The maximum current is V over R, but the current through this as a function of time is the maximum current V over R times 1 minus e to the negative t over tau L, where tau L was L over R. By the way, the unit of inductance is Henry. Unit of inductance is Tesla meter squared over amp, which we call it a Henry. And we denote it by capital H. Now, if you look at what's going on when you have a current here, let's see if you close here, there's a current, let's close the switch, there's current going through here, and you write Kirchhoff law, say V minus L di over dt minus IR is equal to 0. You can move this over, V equals to L di over dt plus IR. And then if you multiply this by I, see what we can say about that. Vi is equal to L I di over dt plus I squared R. Do you recognize any of these terms? What is Vi? What? Power, yes. That is power for the battery. What is this? Power in the resistor. So this is power put into the circuit by the battery, right? This is power taken away, power dissipated in the resistor. So if you look at the conservation of energy, this is the energy put in by the battery per unit time. This is energy taken out by the resistor by unit time. So this must be the energy that goes into the inductor somehow. All right, so the rate of change of energy in the inductor should be this. So if you call it du over dt, which is the power, equal to Li di over dt, then try to solve for the potential energy in the inductor. So multiply by dt and integrate to get u. It's usually called UB because it is related to magnetic field, but then we will see what it is. So if you multiply by dt, you get dUB equal to Li di. And then if you integrate both sides from 0 to UB, let's say, and here from 0 to current I, and then this side becomes UB only. The other side becomes what? 1/2 Li squared. So this is the energy in the inductor. If there's current I going through the inductor, it has this much energy in it. And now we're going to see where this energy actually is. All right? So let's look at a solenoid. And we know L is this for the solenoid. For length L of solenoid, we can say L is mu naught n squared A times L, right? We have L equal to mu naught n squared A times L. And now we want to see how much energy is in that length L of the solenoid. The energy in length L is that much. U, capital U, B is equal to 1/2 L, which is mu naught n squared A L times I squared. Right? I want to write this in terms of the magnetic field inside the solenoid. We know the magnetic field inside the solenoid is what? Remember? It was mu naught N I. So we have this N and I. These are both squared. If I want mu naught squared, I multiply by mu naught, divide by mu naught. So UB becomes 1/2 mu naught, then again mu naught squared, N squared, I squared, A times L, right? And this mu naught squared, N squared, I squared is B squared, right? And so we have UB equal to B squared over 2 mu naught times A times L. A is the cross-sectional area of the solenoid. L is the length of the solenoid. So what is A times L? The volume of the solenoid, right? But so if you divide this energy by the volume of solenoid, you get energy density per unit volume. So, and we call that lowercase u. Energy density, energy per unit volume inside solenoid defined by lowercase b, and is u total energy divided by the volume, which is A times L, which is B squared over 2 mu naught. So that indicates that the energy density actually belongs to the magnetic field. If you have magnetic field inside a volume of a space, it has energy in this space. The same as, remember, this electric energy we had we derived that for capacitor. We said that energy in the capacitor is 1/2 epsilon naught E squared. You see, when you have magnetic field, you have energy in space. When you have electric field, you have energy, and you see they're the same thing. Here you have 1/mu naught, here you have epsilon naught again. Everything is similar, but wherever you had epsilon naught, now becomes mu naught. Later on in the next chapter 32, actually we see that light is electromagnetic wave, can be interpreted as electromagnetic wave, and because we have electric field and magnetic field, light has energy. And the energy of light or energy of electromagnetic field comes from these energies of electric field and magnetic field.